Okay, so for this example, we want to use the plus-minus theorem to show that this set of three matrices is linearly independent. Okay, and we're not going to express it as a linear combination of these three vectors and set it equal to the zero vector, which would be the zero matrix in this case. And then, that's the usual approach to proving linear independence. We want to show that the plus-minus theorem makes it a lot easier to do that. So if we begin with just pick one of these matrices, say this one. Actually, let's do even better. Let's pick two of them. Let's start with these first two and construct a set out of those. Okay, so 2, 0, 0, 0. And then -1, 1, 0, 0. Okay, now right away I know that this set is linearly independent because we've proven a theorem that says that if you have a set containing only two vectors, that set is linearly independent as long as one vector is not a scalar multiple of the other. And I can see that this is not a scalar multiple of this because this entry right here in the first row, second column is a 0. Any scalar I multiply this matrix by has to have a 0 in that same place, but we don't have that here. So these are not scalar multiples of each other. Is linearly independent. Okay, because neither matrix is a scalar multiple of the other. Okay. So the plus-minus theorem, at least part A of the plus-minus theorem, says that if we have a linearly independent set, and if we take a vector that's not in the span of that set and throw it in there, then that new set would also be linearly independent. Well, in this case, this third matrix right here, 3, 1, 1, 3, is the new vector that I want to add to this and get linear independence. So really, this just boils down to verifying that this vector here is not in the span of this set here. And that's not hard to verify because, again, what that means, if this matrix is not in the span of the set containing these two matrices, all that means is that there's no way to write this matrix as a linear combination of these two. And that's easy to verify by inspection because both of these matrices have zeros in their bottom row. Any scalar multiple of these vectors or these matrices will also have to have zeros in their bottom row, and then adding those together is also going to give me zeros in the bottom row. So in other words, any linear combination of these two matrices will have to have a row of zeros in its second row, and that's not what we have here. So this is not a linear combination of these two, meaning it's not in the span of this set. So we can include it, and by the plus-minus theorem, this new set would have to also be linearly independent. So let's write that out, 2, 0, 0, 0, -1, 1, 0, 0, and then this new vector here, 3, 1, 1, 3, is linearly independent because the way I can state this is that the matrix 3, 1, 1, 3 is not an element of the span of this set here, 2, 0, 0, 0, -1, 1, 0, 0. Okay. So that's a little bit sloppy. Hopefully that makes sense. Let's move up a little bit. So another theorem here, it says, again, we're working with a finite dimensional vector space, in particular an n-dimensional vector space, V, and we're going to let S be a set in V that has exactly n vectors. So that means S is a candidate to be a basis here. It has the correct number of vectors corresponding to the dimension of that vector space for it to possibly be a basis. It says then S is the basis for V if and only if S spans V or S is linearly independent. notice the word or instead of the word and. By definition, a basis for a vector space has to have both of these, right? It has to span V, and it also has to be linearly independent. But what we're saying here in this theorem is that if you already know that V is an n-dimensional vector space, and if you have a set of vectors, if you have a set containing exactly n vectors, so you already know that it has the correct number of vectors, it's actually enough to only check one or the other of these conditions for a basis. This theorem says that if one of these conditions checks out, then we automatically get the other one. So let's prove this. Let V be an n-dimensional vector space, and we're going to assume the set S, like we said, has exactly n vectors. Now, this is an if and only if proof, so that means there's two directions to prove. But one direction is pretty much automatic, there's nothing to prove. If S is a basis for V, then S spans V, or S is linearly independent. Well, if a vector space, or if S is a basis, then it has to satisfy both of those. So you could obviously say it satisfies at least one. There's nothing really to prove that direction. We want to go the other direction. So here we're going to suppose S is linearly independent, and I'm going to prove that that implies S also spans V, again using the assumption that S has exactly n vectors. So to prove this, we want to choose some arbitrary vector in V and then show that that vector can be written as a linear combination of the vectors in S. That would mean that this arbitrary vector belongs to the span of S. Okay. So we're gonna do this using a proof by contradiction. We're going to assume that it can't be written as a linear combination of those vectors in S. So if that were the case, then we could use the plus-minus theorem here, and we could say that S union V, so the set that we get from taking this V, tossing it into this set S, would also be linearly independent. But there's a problem with that, because S, we know, has n vectors. So this new set that we got by throwing V in there will have n plus 1 vectors. That's bigger than the dimension of V. And we have a theorem that we talked about previously that says if you have any set that has more vectors than the dimension of a vector space, then that set has to be linearly dependent. So there we have a contradiction with our plus-minus theorem. That must mean the assumption that this V is not in the span of S had to have been false. So we say by contradiction, we've proven that direction. Now we need to assume the other possibility. Instead of assuming S is linearly independent, assume that S spans V. So under that assumption, we're also going to try and proceed with a proof by contradiction. Assume S is linearly dependent. If I can show that that leads to a contradiction, then the implication there is that S is actually linearly independent, and we will have proven this. There exists a vector S, a vector in S, say V, again, that can be written as a linear combination of the other vectors in S. That's one consequence of linear dependence that we've talked about. Okay, but according to our plus-minus theorem, S minus V, so the set that we obtain by taking S and throwing V out of it, will still span all of V. Okay, that set, however, has n minus 1 vectors. And again, using that theorem that we talked about at the very beginning of this section, that's going to imply that the set is actually linearly independent. So that's contradicting our assumption. Or sorry, I said that the wrong way. It's going to imply that this new set can't span V. That's where the contradiction comes in, because our assumption here was that S does span V. So, like we said, we were looking for a contradiction. We found one, therefore S must be linearly independent, making S a basis. It's a really useful theorem because, again, just to reiterate, if you know the dimension of V ahead of time, this means that to verify whether or not a set is a basis is just a matter of determining one or the other condition for a basis. So here, explain why x squared, 2x minus x squared, 1 plus x cubed is not a basis for P3. There's a couple of ways we could approach this. In this case, though, Well, actually, this one, we don't really need this theorem directly, come to think of it, because what is the dimension of P3? Well, it's n plus 1, in this case 3 plus 1, which is 4. If this were to be a basis for P3, I would need at least, or not at least, I would need exactly 4 vectors for it to even be a candidate. We only have 3 here, so there's no way that this could be a basis for P3. Okay? So move on. All right. So one last theorem to talk about here. And there's 3 parts to this one. The proofs of part B and part C are both in your book. I have them written out here. I'm not going to go through these ones in detail. I'm just going to point them out. But I'm going to talk about the theorem, and then your book leaves the proof of part A for an exercise, but I've written that out here, so we can talk about that. So the theorem says that if you have a subspace, if W is a subspace of a finite dimensional vector space V, then W is also finite dimensional. And not only that, the dimension of W has to be less than or equal to the dimension of V. Kind of makes sense intuitively. Then in addition to that, the case where the dimension of W equals the dimension of V only ever happens if W is V. So in other words, if you have a subspace of V, a proper subspace, meaning it's not equal to the entire vector space V, then that dimension would have to be strictly less than the dimension of V. So I only want to talk about the proof of the first part, and then if you have questions regarding the proof of either of these, you can bring them up in the discussion forum. So here we start by kind of ruling out the case where W is the zero subspace. In that case, we defined the dimension of W to be 0 in our definition for dimension, so that takes care of itself. So we're going to assume that the subspace W is a non-zero subspace, meaning it has a non-zero vector in it. I'm going to call that non-zero vector V1. Now we know that the set V1 is linearly independent because any set containing only one vector is always linearly independent. And if we were to look at the span of that set, if that span turned out to equal W, then V1 would be a basis for W, right? And that would mean W has dimension 1, so it's finite dimensional. However, if the span of that set is not equal to W, then that would mean that W contains some vector that's not in the span of this set. Let's call that V2, okay? By my plus-minus theorem, if I took that V2 and tossed it into the set with V1, creating this new set, V1, V2, it's possible that that new set might span W. Okay, and if it does, then W is finite dimensional. It would have dimension 2 in this case because V1, V2 would form a basis. Remember, the plus-minus theorem guarantees that constructing the set this way maintains linear independence. And then if the span is equal to W, there's both conditions for a basis right there. However, if V1, V2 is not a basis for W, then you can keep doing this. So we can keep finding vectors. If this is not a basis for W, the implication is that this does not span W, meaning we could find vectors in W that are not in the span of this set, throw it into this set. We still get linear independence by our plus-minus theorem, and then it's possible that the span of that set will equal W. If not, you keep going. You keep finding new vectors not in the span, toss them into the set, and keep checking. Now, if we suppose for a second that W was not finite dimensional, an important aspect of this process is that the plus-minus theorem guarantees that every time we toss in one of these new vectors, we continue keeping linear independence every time. If W is not finite dimensional, then this should never come to a stop, because if it does come to a stop, that means we found a finite basis for W. So the assumption that W is not finite dimensional means we can keep throwing in vectors into this set and never actually get it to span W. The problem with that is that we're assuming W is a subspace of a finite dimensional vector space V. If that's true, eventually this set is going to become the size, or it's going to have enough vectors that matches the dimension of V. As soon as we exceed that value, we know again from that theorem at the beginning of this section that set is going to be linearly dependent. Any set with more vectors than the dimension of a vector space is automatically linearly dependent. That contradicts the fact that this should continue to be linearly independent forever. What that's really contradicting is the assumption that W is not finite dimensional. So by that contradiction, then we would have to say that W is finite dimensional. That wraps that one up. And again, I'm going to leave these two proofs for parts B and part C for you to read. And again, I'm happy to answer questions on those if you have them.